time to take our practice in a whole new direction. We're going to be working with vectors. These are objects which have both a magnitude and a direction and form an important part of understanding geometry and will be very useful as we continue in our exploration through multivariable calculus. It's important that you do a lot of practice with this so that you can start to develop the important geometrical intuition which will be underlying our calculus going forward. So, if you're following along with the video, make frequent use of the pause button. So you can pause, try as much on your own as you can, and when you need me, just unpause me. I'll come along and we'll figure it out together. Well, let's begin. Our first problem. Find all. Oh, maybe there's many. Find all values A so that, well, there's this vector, and we know it's a vector because of these angled brackets, 2 minus 1, 1, plus some multiple of some other vector is a unit vector. Okay, so in other words, we really have like this family of possible vectors. There's a whole range of vectors it could be, and we're trying to say, well, are any of them unit vectors? Can we figure it out? So let's think about what the picture is. Well, first off, since we're in component form, let's merge it into a single expression. So, in this case, we could say, look, this is really the same as, in the first slot, we would say 2. Now here, this a distributes through, so 2 minus 4a, comma, minus 1, and then plus a, and finding the last one, 1, and minus 2a. So there we go. That's another way to write this vector. And now we have our vector. We say, well, let's take a look. We want it to be a unit vector. So a unit vector is a vector which has length 1, because remember, that's the word unit. Unit means 1. So we say, well, look, we really want the magnitude of our vector, 2 minus 4a, minus 1 plus a, 1 minus 2a, equaling 1. Now, for convenience, the magnitude involves a square root. Well, we'll just square both sides. So we just need the square equal to 1 squared, which is still 1. Okay, so what is that? Well, if I'm squaring the magnitude, it says square the first entry, so 2 minus 4a squared, and then square the second entry, negative 1 plus a squared, and you square the last entry, 1 minus 2a squared equals 1. Now, to be patient. All right, expand. So, b squared, 4, minus 2ab, well, it'll be a is 2, b is 4a, so it'll be minus 2ab would be 16a, and then the term on the end, 16a squared. Okay, so that's the first piece. Here, 1 minus 2a plus a squared, that's the second piece. Then 1 minus 4a plus 4a squared, and all that equals 1. All right, got it. Well, time to put everything together. So, let's see. How about the a squareds? There's 3 of them. 16a squared, 1a squared, and 4a squared. Okay, so that would give us 21 of our a squareds. There's a minus 16a, a minus 2a, and a minus 4a. All right, well, that would give us a minus 22 times a. Then for our constants, we have a 4, 1, and a 1. That's 6. But then we have to take this one into account. When we put it over, it's going to be subtracting 1. So that leaves us with 5. So that equals 0. All right, so there we go. So we just have to solve this. Well, what do we hope? Well, we'd hope, if we were lucky, that it factors. So let's think about it. What would it factor as? Now, in some sense, if it did factor, we see, aha, the fact this is a 5 tells us on the end, well, it would have to be something like a 5 and a 1, because there's only one way to break 5 apart, because 5 is a nice prime number. Because this is being added, they both have to have the same sign, and because that's a minus, we have to have a -5 and a -1. And then we have to have an A and an A. The only thing that we don't know is the coefficients. So we start thinking about, okay, what do we need to have the coefficients do? Well, they have to multiply together to give 21. And 21 doesn't break apart that easily. So it's 3 times 7 or 1 times 21. So we just start trying things. So if we had 1 and 21, that would be really bad because see, the 21 times 5, huge. Forget it. If we had the 21 and the 1, we have a -5 and a -21. Out. Doesn't work. Let's see. Suppose we had here a 3 and a 7. Well, that's -35 minus 1. Forget it. Okay. What if we, what's 7 here and 3 here? What about that? Let's check that. 7 and 3. Does it work? Well, 21a squared, that's good. -7 minus 15 is -22 and plus 5. It does work. If you'd use the quadratic formula, you would end up at the same set of answers, and that's okay too. All right, so lo and behold, we see, aha! This tells us what? Well, either 3a minus 1 equals 0, which happens at a equals 1/3, or 7a minus 5 equals 0, which tells us that a would have to be 5/7. So there's two possibilities, 1/3 and 5/7. And that's it. Those are the two answers. So there's two of them. Now, on a side note, there's sort of an interesting geometrical interpretation to this problem, which we don't need to know in order to answer it, but, you know, it's fun to know things. So what's the interesting geometrical interpretation? Well, suppose we think of vectors where we say, look, let's move it so that the start of the vector, or you might call it the tail of the vector, is at the origin. What would the set of all unit vectors be? Well, that would say, look, if you start from the origin and go out distance 1 in any direction, well, what you end up with is you end up with a sphere. So somehow unit vectors are nicely correlated with points on the sphere of radius 1, the unit sphere. So, all right, if we think about that, that's fine. Now, here's the more subtle thing, which will make more sense in the near future, but we can go ahead and talk about it now. If we think about what's happening with these vectors, well, with those vectors, what you have is essentially you're perturbating along some sort of, you're starting at some particular vector, and then you're just perturbing it forward and backwards by another vector. So it turns out that if you do the same process, you know, let's put something where the start is always at the origin and then just follow along, where does the head of the vector move? Well, the answer is that it moves along a line. And so in essence, what's happening here is we're trying to find the places where a line is intersecting a vector. Sorry, a line is intersecting a sphere. That's what it turns out to be equivalent to, which means that for any problem of this nature, there will only ever be 0, 1, or 2 answers. 0 would be if the line completely missed the sphere. 1 is if it just barely touched the sphere. It was tangent to it. And 2 is similar to what this is, where it actually pierces the sphere in one side and out the other. But we'd never hit it 3 times, because you can't have a line that hits the sphere 3 times. Again, you don't need to know this to solve the problem. It's just sort of an interesting geometrical interpretation, which will make a lot more sense in a very near future. So, all right, good. Well, let's do another problem. Switching topics to midpoints. Given points a equals 1, 2, 5, b equals 3, 6, 1, c equals 4, 3, minus 1, find the point D. so that the line segment containing A and B has the same midpoint as the line segment containing C and D. So this is a problem about midpoints. Now, let's sort of get an intuition about what's going on here. So we have some points. So let's just go ahead and mark them. We have A, B, and maybe we have C, and then we have some unknown point D. Now, what do we know? We know that they have a common midpoint. See, it says it here, uses the word same midpoint. So there's a single midpoint for A and B as there is for C and D. Well, we know what A and B, where they're at, so we know where their midpoint is at. So we can actually indicate that in our picture here. We say, well, look, A and B have a midpoint, and we can mark it. So here's their midpoint. We don't know what it is yet, but we'll compute it in just a moment. We can. And now we say, well, perfect. You see, from C out to our midpoint, that's the halfway point to getting to D. So we can imagine, like, well, whatever I did from C to the midpoint, if I keep doing that, midpoint out here, that will leave us at our destination, to D. So let's sort of work our way up. Step one, we're after the midpoint for A and B, because that's the midpoint we can compute. So we know our points are 1, 2, 5, and 3, 6, 1. So the midpoint is found by more or less averaging each entry. So what's halfway between 1 and 3? So that's our x coordinates. Halfway between 1 and 3, well, is 2. You can also find it by adding the two numbers and dividing by 2. Well, between 2 and 6 would be 4, and between 5 and 1 would be 3. So 2, 4, 3, that's the midpoint from A to B. Now, how about our point C? We know where C is located. It's located at the point 4, 3, negative 1, because that's what we're told. So we can think to ourselves, okay, I'm at 4, 3, negative 1. How did I move to get to 2, 4, 3? Well, that's a vector. That's talking about change. How did I change to get from the C to the midpoint? So we look at it and say, okay, well, this vector here, well, in the x coordinate, we went from 4 down to 2, which means that we went down by 2. We went from 3 to 4, which means we went up by 1. We went from negative 1 to positive 3, which means we increased by 4. So to go from C to the midpoint, the vector that does that is negative 2, 1, 4. Well, that means that this vector, which gets us from the midpoint to D, is the same vector, negative 2, 1, 4. So we say, okay, well, starting at our midpoint, we have 2 go down by 2. So that would be 0. 4 go up by 1 would be 5. 3 go up by 4. That would be 7. And therefore, our missing point is located at 0, 5, 7. And that's it. We're done. Good. So this is nice. It's sort of like, okay, how do I find what I'm looking for? What do I already know? Oftentimes, you can start by saying, well, let me draw a rough picture, and then let's fill in what we know and figure out how is the missing information related to what we already have, and how can I get there? Wow. In our case, it's like, well, look, I can get from C to the midpoint. Okay, let's repeat that, get from midpoint to D. So, all right. Well, let's try our hands at another problem. So, here we go. Oh, a word problem. This will be good. There is a two-stage rocket which will move through the XY plane. So 2 stages means that there's going to be 2 things that happen. So what's going to happen? Well, initially, the rocket's located at 2, 1. In the first stage, for every unit of fuel, used, it will move 5 units in the x direction and 11 units in the y direction. In the second stage, for every unit of fuel used, it will move 2 units in the x direction and 5 units in the y direction. Now, given that the goal is to get the rocket to the point 12, 24, determine, if possible, how much fuel should be used in each stage. So what's happening here? Well, in one stage it's going to go and then it's going to finish, and then it's going to sort of move in a different direction. So our goal is to say, well, how do we balance these two different stages? What's the right amount to spend in our first stage? What's the right amount to spend in our second stage? So that the net result gets us to where we want to go. And how does this have to do with vectors? Well, in some sense, what we can think of is that we're talking about movement. And we can say, well, let's think about our stages. So let's talk about our first stage. In our first stage, what do we have? Well, we're going to be talking about, we're changing. See, movement is about change. So we move 5 units in the x, 11 in the y. So what we have is we have 5, 11, and we'll times that by A. So A, we can think of as how many units of fuel. However many units of fuel we have times 511, that's going to be the net change that we're going to have as a consequence of that first stage. In the second stage, what happens? Well, in the second stage, we're going to do the following. We're going to move 2 in the x direction and 5 in the y direction. So 2, 5. So that's going to be the change in stage 2. So we have stage 1, stage 2, and we say, well, what do we want? Well, we want to know what's our total change. So we say add the two of these together, and that's going to be the net result. However much we spend in stage 1, combined with however much we spend in stage 2, our total change will be given by this expression. Now, what are we trying to do? We're trying to get to 1224. Now, be careful. That doesn't mean we're going to set this equal to 1224, because where do we start? We start at 2, 1. So in terms of the picture, we're starting here at 2, 1, and we want to get over here to 1224. So what we're trying to do is trying to say, well, what's the total change that we're looking for? Well, we want to get the net change is this vector. Well, how do we do that? You say, what's the difference in the x-coordinates? That would be 10. What's the difference in the y-coordinates? That would be 23, right? 12 minus 2, 24 minus 1. Okay, there we go. Now we have more or less a plan. We say, look, that's what we need to figure out. We need to figure out what's the right combination to make this true. Well, now let's sort of say, what is this telling us? Let's combine this vector to one vector over here. So we can also say we have 5 times A plus 2B, or is it not 2B? No, it's 2B, right? 2 times B, comma, 11 plus 5B equals 10, 23. Now, a very simple observation, so simple it might not seem useful, but it is the following. 2 vectors are the same if and only if all the entries are the same. So what needs to be true is that we look at this expression, the first entry has to match the first entry. The second has to match the second. So we can say 5A plus 2B has to equal 10. And 11 plus 5B, where did that 11 come from? It's 11A. I am so sorry. So foolish. Don't, be careful. Be careful. Oh, all right. back to our regularly scheduled solving math. Here we go. 11a plus 5b has to equal 23. Good. Now what? Well, two equations, two unknowns. This is great. This is the type of stuff that we love. And we sort of say, well, how do you approach it? Well, there's lots of ways to approach it. Now, the way I like to approach these problems is through cancellation and say, well, let me find ways to cancel things out. So I'm going to combine these two equations in some way so that one of the two variables cancels. For a second, let's focus on the b variable. So I have 5a plus 2b equals 10, and 11a plus 5b equals 23. Now, what do we do? Well, we say, well, if we want to cancel the b's, we should find a way to scale the equations so that what's in front will be the same size but opposite sign. So, for instance, one thing we can do is we could say, well, let's take the first equation, multiply it by 5, and we'll take the second equation and we'll multiply it by -2. Now, if we do that, what will happen? Well, you'll see we'll get 5 times 2b is 10b, minus 2 times 5b, minus 10b. So the net effect is we have no more b's. They've canceled out when we combine together. Here we have 25a minus 22a. Well, that's 3a. Yeah. And then 50 subtract 46. Well, that's 4. Well, that's nice. That's actually pretty simple. So that lets us say that a is 4/3. So that's how much we should spend. We should use 4/3 units of fuel moving in the first stage. Now we need to go into stage 2. So for that, similar idea. We say, great, well, let's do the same process, but now let's think about what we can do. Instead of canceling the b's, we want to cancel the a's. So what can we do in this case? Well, we look and say, well, again, we want to get these the same size but different sign. And so for that, well, let's multiply the first equation here by 11 and the second equation here by -5. So you'll see we'll get 55a minus 55a, which means that there's no more a's. The a's will cancel out by design. 22b minus 25b is a -3b. Well, that's okay that it's negative. We'll fix that later. Equals 110, right? 11 times 10, 110. 5 times 23, well, 5 times 20 is 100, and 5 times 3 is 15, so that's 115. 110 subtract 115 would be -5. Well, that's good. They're both negative. So B would be what? Well, 5/3. So that's what B is. So we come to the conclusion that it should be possible. Now, when would it not be possible? Well, it might not be possible if one of these values were negative, because it can't be, well, I'm going to use up -5 gallons of fuel while I'm driving from point A. No, you can't use a negative amount of fuel. Fuel has to be a positive amount that gets used. But in this case, both stages use a positive amount, so that's perfectly fine. Nothing strange going on. So we're going to use 4/3 units in stage 1, and we're going to use 5/3 units in stage 2. And a grand total of, we're going to use 4/3 plus 5/3 makes 9/3. And so, and there we go. That's a reasonable amount, and it makes it very efficient. We can use just the right amount to get from where we start to where we want to go. Good. Okay, well, let's try another problem. So, let A, B, C, D be the vertices of a parallelogram. show the midpoint of A and C is the same as the midpoint of B and D. And there's a hint, which is good. Use vectors to get to the respective midpoints starting from A. So let's think about what's happening here. Well, let's draw ourselves a diagram. We have A, over here is B, and then we go up, there's C, and it's a parallelogram. And so we have the sides are equal. A, B, parallel over here, and these sides are parallel as well. So what's our goal? Well, our goal is to look at the midpoints. So we want the midpoint of A and C, this right here, to match the midpoint of B and D. So that's what we want to argue. Why do the midpoints have to be the same? Well, we start by saying, let's think about things in terms of vectors. So let's call the vector from A to B, for a second here, just for shorthand, we'll call it U. Now, what about this vector up here that goes from D over to C? What should that be? The answer is, it's also U, because you'll see there's this notion right here, parallel. These are parallel sides, which means that to get from that side to that side, everything's parallel. So I can just like lift this vector up, put that vector down. It's the same vector. Vectors aren't tied to locations. We really can move things around. So it's just like we moved it over, since it's the same direction, same length, same vector. On the other hand, we say, well, this vector going up here, we'll call that vector V. And of course, since things are parallel, over here, this is also V. Now there's two more vectors to mark. And so what are they? Well, they're the ones that correspond to the diagonal. So let's talk about this vector here. Well, this vector, I start at A, I want to end at C. Well, I can move along the sides which have already been labeled as vectors. U first and then V. So this is U plus V. One more side to label. Once we have that, then really we just have to sort of examine this closely and try to spot a nice pattern. Okay, so let's label our last side. So let's do this one. Here we go. Now the question. What happens is I start at B and I want to get to D. How can I do that? Well, let's think about moving along vectors. So suppose I just think about moving along the side. I could, for instance, start and move along B to C. That says, well, that just says go for the vector V. And then I could go from C to D. But here's the key. Notice what's happening. I'm going the wrong way, going backwards. What does it mean when I go backwards? Well, when I'm going backwards over something, what that means is I'm doing the negative. So if we think of it this way, it's V minus U. So that's this last piece, V minus U. All right. So with all our pieces in play, we can say the following. So from A to the midpoint of AC. Well, what would that be? Well, I can just go along this vector and say, well, that vector from A to C is U plus V. I start at A, so to get to the midpoint, I only go half the length of the vector. So that would be 1/2 U plus V, which is 1/2 U plus 1/2 V. So that tells me here's the rule to how you get from A to the midpoint of AC. You take half of U, you add half of V, and you're there. Well, now what we do is let's repeat it. So from A to the midpoint of BD. Well, let's just follow a route to get there. Let's go from A to B. So that would take us U to do that. A to B. And then B, we don't want to go all the way across. We go halfway across. So plus halfway in the direction V minus U. So again, what we're doing here is we're focusing on how do we get from one place to another. When we talk about how do we get from one place to another, that's talking about how do you change your location. It's vectors. Well, what do we have? Well, if you look, you have a U, and then you have a minus a half a U. So if I combine the U and a minus a half a U, that's a half U. And then there's a half V. And now we pause and say, well, to get from A to the midpoint of AC, I need to go half U plus half V. To get from A to the midpoint of BD, it's the same change. Well, if I start at a point and I change in the same way, I'm going to end up at the same point both times. So we now can conclude that these are equal, and therefore points are going to agree. And therefore, that's the proof. That's the proof. We start at the same location. We always start at A. We move by the same amount, and therefore we must be at the same point. Okay, good. And actually, it's not so bad. This is really just saying, look at change, understand change. If you can think about how we can combine change, things work really nicely. All right, well, let's do one more problem. Saving the best for last, maybe. We'll see. So we're given the spheres x minus 7 squared plus y plus 3 squared plus z squared equals 49, and x plus 3 squared plus y minus 7 squared plus z plus 5 squared equals 100. So you have two spheres. Find the equation of the largest sphere that fits inside both spheres. So, in some sense, we're saying, look, these spheres, it sounds like what's happening, sort of the picture is we have a big sphere, and then we have a smaller sphere that's somehow offset. So this is our big sphere. We'll say that's the sphere with radius 100. Here's the small sphere with radius 49. And our goal is to say, look, there's some sphere here that's the largest sphere you can squeeze into both of them. What sphere is it? All right. Now you might say, Steve, your picture here is wrong. You've drawn circles, not spheres. Well, that's probably not a bad thing. Oftentimes when you're trying to do a problem, you say, look, if it's throwing you off because it's three-dimensional, think of the two-dimensional analog. So instead of spheres, think circles. So let's start thinking about what must be true. Well, one of the key ideas with spheres is oftentimes you focus on the centers. How do the centers relate? So if we think about our centers, we can think about our picture here. So in the big sphere, where's our center? Well, it would be at -3, 7, -5. In the smaller sphere, we would be at 7, -3, and 0. So those are our two centers. Now, what will happen is if we think of our geometrical intuition, well, we want to go directly between the centers because the biggest sort of overlap is going to occur right between the centers. So we say, aha, good news. We know that our new sphere is somehow there in the middle. So that's what we want to understand. Now we have to start thinking about a couple of pieces of information here. Well, let's think about what we know. We know the radius of the big sphere is 10, because see, that's 10 squared. So this distance, is 10. We also know the radius of the small sphere is 7. So that says from the small center out to the edge, that's 7. Well, and now we start thinking, okay, if that's 10 and that's 7, how do we use that information? Well, what's something else we can find? Let's think about things we could find that might be interesting. And one thing that I think would be interesting is let's talk about this distance between the two centers. All right, so distance between centers. Well, for that, we can start as a stepping stone. We can say, well, let's actually think of it as there's a vector. And it doesn't really matter where we start. Let's just go from here to there. So let's think of the vector from the center of the big sphere to the center of the small sphere. The length of the vector is equal to the distance. So what happened? We went from -3 to 7. So we'll have our vector, call it v. The x-coordinate went up by 10. Then we went from 7, and then we went down to -3. So we decreased by 10, so -10. And then we went from -5 up to 0. So that was an increase of 5. So the distance is the same as the length of the vector, because the distance between the points is the same as the length of the vector connecting the points. So that's going to be the square root of 10 squared plus -10 squared plus 5 squared, which is the square root of 100 plus 100 plus 25, or the square root of 225. Now, it would be nice if it was the case that this number was a perfect square. And it's nice. Do you recognize this? It's not one that's very common. We don't see it very often. It's 15. So that tells us that if we look at the distance between the centers here, that's 15. Now, let's put this all together and see what that tells us. We know if we go just between the centers and nothing else, that's distance 15. If we go from the center of the big sphere out to its edge, that's 10. Center of the little sphere out to its edge, that's 7. If we stare at this, we say, aha, look at this overlap. This overlap would be the small sphere. And so we could say, well, if I go 10, back the diameter of the big sphere, then 7, that would get me between the two. So this center distance here, this diameter, would be the same as adding the two radiuses together and subtracting 15. So the diameter of our sphere that we're after is going to be what? Our diameter is going to be add the 2 radii, subtract 15, which means it's 2. So this distance is 2. Now, if that's the diameter, the radius is half that, and therefore the radius of our sphere is going to be 1. We've made progress. So, perfect. So far, so good. Now, the other thing to note is that nothing we've done so far requires vectors. So you might say, okay, where has vectors come in? They haven't really yet. We could have done all of this with just distance. Now, there's another important thing, though. We're not done. You see, we know the radius of the sphere, but we don't have enough to give the equation of the sphere because we still need the center. So we need to center ourselves and ask, where is our center? Now, let's think about what's true. Well, if we look at our picture here, we say, if I want to get to the center, I know that the center lies on the line that connects the other two centers. In other words, here's the key idea. the direction from the big sphere to the little sphere is the same as the direction to the overlapping part. The only change is I don't go as much. So I've sort of scaled down my change. So the question is, how far do I need to go? Now, originally, what did I do? Well, I went a distance of 15. So our original vector is length 15. How far do I need to go now? Well, let's think about it. I'm going to go 10 to get to the edge of a big sphere. To get to the center, I go back 1. So 10 subtract 1 means I need to go 9 units. So instead of going 15, I need to go 9. So here we go. The vector from the big sphere to center of the overlap, well, we're going to take our original vector between the two original spheres. We're going to scale it down. So we're scaling it down by its magnitude. The reason we scale down by its magnitude is because we want to make it a unit vector which gives direction. Unit vectors are direction. This points in the right direction, has length 1. Now we turn around and we multiply this by 9 because that's how far we need to go to get to our new center. So, well, we can simplify things. So 9 over 15, for instance, is really 3 over 5 because they can take out a factor of 3. So that's 3/5 times 10 minus 10, 5. Well, multiply it through. And you can see 5 goes into everything, so it actually will be really clean. So 3/5 times 10 is 6 times negative 10, negative 6, and times 5 is 3. So this 6 minus 3, that is the change from our current center of our big sphere to the center we're looking for. So that's not our center, but it's how we get to our center. You see, oftentimes you might say, well, look, maybe I don't know my answer, but can I get to my answer? And if we can figure that out, then we're in good shape. So we need to figure out if I start at negative 3, 7, negative 5, and I move by 6, negative 6, 3, then where are we at? So our new center, we're almost there. So our new center is going to be, well, negative 3 plus 6, 3. 7 minus 6, 1. Negative 5 plus 3, negative 2. So that's our new center. But we also had our new radius, and we put them together. So x minus 3 squared, y minus 1 squared, and z minus 2, which makes z plus 2 squared, equals 1 squared. And that is the equation for the sphere, which is the overlap between our two original spheres. It's a really beautiful problem. I love this problem because there's so many little things going on. It's about geometry. Can you see what's the picture? How does it look like? What does it mean? You need the distance. Look at the overlap. How do you move from one center to another center? And then, of course, that the numbers work out so nicely. It's almost like it was meant to be. And this time, I think it was. Great problem to finish on. Thank you for working and staying here to the end. And keep it up. You're doing great. And we'll see you in more sessions, right? Yeah, all right. Come on back.